Hello, and welcome to Significant Figures. This is your notes and practice session. You should open up the Google Doc that's associated with this video, and I will cue you into the practice time where you work out problems based on the ideas that I'm sharing. Okay, so go ahead and get that document up, and I'll run through the ideas behind significant figures and significant digits. The first question is, what are significant figures? And the answer to that question is very specific. They're not things like important things. They are specifically all of the digits that are in a measurement that are known, plus a last digit that we estimate or is estimated for us. These are also known as significant digits or sig figs. Here's an example. In the measurement 10.9 centimeters, the 1 and the 0 are known or certain. We use those interchangeably, and the 9 is estimated. All three digits, 1, 0, and 9, are significant digits. So this measurement has 3 sig figs. Why do we use significant figures in chemistry? The answer to that question is pretty simple. Let me move this around a little. A measurement or calculation has to be reported or recorded showing the correct number of significant digits so that the value reflects the precision of the instruments used to measure. One of the examples that I share is if we have 6 significant digits for a density that was taken with the type of laboratory equipment that we have in our laboratory, then that's like NASA level significant digits, and we don't have the capacity to measure to that level. So we are going to show what level we can measure to. Significant figures do become easier to understand as you use them throughout the course, and I will keep reminding you and asking you about significant figures as we do problems and calculations in class. They are extremely important. Learn the rules and use them, or be haunted by significant figures for the year. And just an aside, this significant figures and understanding them can make the difference between, say, an A and a B in chemistry or a B and a C in chemistry. That's how many points are worth that and how much we continue to use them throughout the year. What does a chemistry student need to know about significant digits and be able to do? Here's what you need to know how to do. Determine the number of sig figs in a recorded or given measurement or calculated value. Identify significant digits as certain or estimated versus non-significant digits. And correctly record measurements which show all significant figures using digital and non-digital, or what we call manual measurement tools. You also have to calculate values using measurements and record the calculated value with the correct significant figures, ensuring it is rounded as needed. And we will go through all of these different things and show examples. You also need to convert values to and from scientific notation, keeping all significant digits. Here are the rules that tell us what are significant digits in a measurement and how many are there. The easiest rule to remember is that if we have non-zeros, those are always significant. For example, the value 1,423.88 has 6 significant digits because all of those digits are non-zeros. Zeros, on the other hand, can be significant or not, and we're going to use a series of guidelines to help determine if zeros in a measurement are significant. Here are the rules for zeros. The first type of zero, we have nicknames for these. They are called tweeners. These are zeros between non-zeros. Tweeners are significant. For example, 2003 has 4 significant figures, and 102 has 3 significant figures. So in 2003, the 2 zeros in the middle are significant because they are tweeners between non-zeros. With 102, the 1 0 in the middle is significant because it's between two non-zeros. The other type of zero are lefty zeros. These are zeros to the left of all non-zeros. Lefties are not significant. For example, 0.6104 has 4 significant figures. The first zero is not significant. It's a lefty to the left of all non-zeros. But the tweener zero, between the 1 and the 4, is significant. The value 0.003 has 1 significant figure, that is just the 3. All of the lefty zeros are not significant. The other type of zero we call righties. Righties are zeros to the right of all non-zeros. They are only significant if a decimal is written somewhere in the measurement. A measurement with a decimal indicates the zero at the end of the value have been measured and are significant. Without the decimal, the zeros at the end of the measurement have not been measured and are not significant. For example, 5.00 has 3 sig figs because the zeros are to the right of the 5 and the decimal point is written in the value. Another example is 3,400. It has 2 sig figs as written, and the 3 and 4 have been measured, but the zeros have not. The value 600 with a decimal following the last zero has 3 sig figs because the decimal indicates the values have been measured to the ones place. Second part, what are the significant digits, in a measurement and how many are there? Counted and exact values have an infinite number of sig figs. So this will come up when we have things like number of times you write your name, or number of students, or number of pencils that are counted in different calculations. Those are an exact value and they have infinite sig figs. For example, here are some examples of counted values. 18 students, 5 written names, 1,000 grams equals 1 kilogram. Those are all values with infinite sig figs. This will be especially important when making calculations and determine the number of sig figs in the solution. In scientific notation, the first factor includes all significant figures, and the second factor does not affect significant figures. So for example, 2.30 times 10 to the 15th has 3 sig figs. That comes from the 2, 3, and 0. 10 to the 15th does not contribute to sig figs. Now is the first time for practicing. So what you need to do is go to the Google Docs and complete the problems in section 1. That's A through F, following the instructions for completion. And just a heads up, you're being asked to highlight all of the significant digits, underline the significant digit that is the estimated one, that's always the rightmost of the significant digits, and say how many significant digits there are for a particular value. Refer back to the rules that are written both on that document or in the slideshow as you need, and pause the video now and complete. Come back after you finish section 1. Welcome back. You should have completed section 1's problems, and that would be A through F. Okay. Now we're going to talk about significant digits and measurement. First, we'll refer to digital measurements, like the scales that we've been using so far in the chemistry classroom. Okay. All of the displayed digits, with the exception of lefty zeros in a digital measurement, are significant. The rightmost digit has been estimated by the machine. Okay, so for example, if you measured out a mass of iron in the separation of mixture lab that was 2.35 grams, then all of those digits are significant, and the last digit, the one 2 places to the right of the decimal, the 5, would be estimated by the machine. Remember that the estimated digit is still a significant digit. And in chemistry class, we typically use digital scales, pressure sensors, and temperature gauges. Always record digital values as shown on the scale and don't leave off the final 0 or zeros. Here are some examples of digital measurements. Your scale measures 1.56 grams. This value has 3 sig figs, and the 6 is the estimated digit. If you get a value of 0.24 grams, the measurement has 2 sig figs, the 2 and the 4 is the estimated digit. Remember, the 0, which is a lefty 0 to the left of all non-zeros, is not significant. If your measurement is 12.00 grams, the measurement has 4 sig figs, and the final 0 is the estimated digit. Remember, those zeros are righty zeros, and because there's a decimal in place, they are significant. Next, you're going to practice. Go to the Google Doc and complete problems in section 2, that's G through L, following the instructions for completion, similar to the first section you did. Pause the video and return after completing section 2. Okay, so we're back and recording. Let's make sure we're doing that. Okay. All right, next, with significant digits and measurements, we're going to look at non-digital or manual measurements. When we have a manual measurement such as a metric ruler or a graduated cylinder, these are manual measurement tools where we have to read and get the values from the measurement tool. It's not digitized for us like the scales are. The markings on the manual measuring tool provide certain values, and an estimate must be made for the digit smaller than the markings. So what I have here is a metric ruler, and I can see that the markings on this metric ruler, the smallest markings are in the millimeters, okay? It has centimeter markings that are the larger markings, and then it has millimeter markings, okay? I have certain values down to the millimeter, and I would need to then estimate to the 1/10 of a millimeter. On this tool, which is a graduated cylinder, I have values here. I have markings that show me to the milliliter values, so I would need to estimate to a 1/10 of a milliliter. If length is measured and the smallest markings are centimeters, then it's the millimeter value, the 1/10 of a centimeter, that is estimated and recorded. If a graduated cylinder's smallest markings are millimeter, like this one, the measurement should be recorded, including the estimate of 1/10 of a milliliter. If the smallest markings are extremely close together, then the estimated value can only be determined as the next digit of 0, which is the smallest line, which is on the smallest line, or 5, which is halfway between the smallest lines. So I'll do an example of this because you're going to be asked to do this on the practice. So I have a calculator here. I'm going to measure the length of the calculator. So I line it up with the 0 on my scale and look for markings. And I can see that this goes to the certain, which is 12.9 centimeters. And it looks like it's halfway between the 12.9 and the 13. So I would call that 12.95 centimeters. Okay, so that's using the markings on the scale as the certain, and then the values between I have to estimate. Now with this graduated cylinder, put that where you can see it, I'm going to be looking at this. I have to set it onto my desk and move so that I can be at eye level with this. And I can see that the water that I put into here is at 20.8 between the 20.8, or sorry, between 28 and 29 milliliters. And to me, it looks like the value is actually 28.3 milliliters. Okay, so I was looking at that. And you'll be asked to look and consider the values that are coming up. The measurement of 10.9 centimeters given in the example above indicates that the tool was used for measuring had markings every centimeter, but the 1/10 of a centimeter was estimated by the student. Just a note, different individuals might actually see or have an estimate that is different, but it should be close. If I see a value that is 12 or 28.3 milliliters for my graduated cylinder, then very likely somebody else, if they're measuring it in the same way and carefully, should not see 28.9 milliliters. Remember that the estimated value is one of the significant digits. In chemistry labs, metric rulers, graduated cylinders, and the thermometer values, not the temperature probe, which is digital, but the thermometer values should be read and recorded using a final estimated digit. Now pause the video and go on to complete the practice problems in section 3. There are 3 diagrams following the instructions for completion. Welcome back. All right, on to the next. This is calculations using significant figures. And this will be something that we use throughout chemistry. Need to make sure that you are confident with the rules for calculations. So first off, rounding rules. You've done rounding before, and you need to make sure that you understand the rules that we use for rounding. They're probably similar, but there may be some specifics that you haven't looked at before. What we're going to do when we need to round to the last significant digit after our calculation is we're going to round the last significant digit up if the digit to the right of that last sig fig is a 5 or greater. If the digit to the right of the last sig fig is 4 or less, then the last sig fig stays the same. If the digit past the last sig figs are to the right of the decimal, then they would be dropped and not replaced with a 0. If the digits past the last sig fig are not to the right of a decimal, a 0 is placed for those digits. Remember, don't put a decimal after the zeros on them. For example, 1.257 rounded to 3 sig figs will round to 1.26 because the 7 after the 5 rounds it up. The value 4,789 rounded to 2 sig figs will be 4,800 with no decimal. Remember that 1.145 rounded to 2 sig figs is 1.1, not 1.2, because the 4 is not a 5 or greater. Now is the time to pause the video and go to the Google Doc and complete problems in section 4, M through P, following the instructions for completion. Pause the video and return after you complete that section. Welcome back. Next, we're going to look at calculations for using correct significant figures with the addition and subtraction rules. We'll get into the rules for multiplication and division in just a little bit. These calculations are based on place value of the original significant digits, not the number of sig figs. That's really, really important. So you need to realize that this is a place value and not number of sig figs. There are several ways of considering this. The textbook explains that the answer to an addition or subtraction calculation should be rounded to the same number of decimal places, not digits, as the number with the least number of decimal places. This works well if all of the added and/or subtracted values have digits to the right of the decimal. For example, 1.12 plus 1.241 plus 1.1321 adds to 3.4931 and should be rounded to 2 places past the decimal, so the correct answer is 3.49. Addition and subtraction rules continued. These rules will be used most often with mass values from different scales or temperature conversion values. For example, if we have 25.5 degrees C converted to Kelvin, we add 273 to the 25.25 degrees, or sorry, 25.5 degrees, for a non-rounded value of 298.5, which rounds to the ones place with 299 Kelvin. So now you're going to practice. Remember that this is place value based. Complete the addition and subtraction practice problems in section 5, Q through T, following the instructions for completion. Pause the video and return after completing section 5. So pause now and complete those problems. Welcome back. We're going to continue and look at calculations for correct significant figures for multiplication and division. So as I said before, when we add and subtract, that's based on place value. Multiplication and division rules are based on the number of significant figures in anything multiplied or divided. So what we're going to do when we find a calculated answer is round the answer to the same number of significant digits or figures as the least number of sig figs in any value that was multiplied or divided. Keep in mind that exact values have unlimited or infinite sig figs, so they will not determine the number of sig figs in an answer. For example, 2.34, which has 3 sig figs, times 12.02, which has 4 sig figs, will have an answer rounded to 3 sig figs. The calculator value of 28.1268 will round to 28.1 for the correct significant figures. And sometimes in these problems, you'll be asked for a calculator answer, which has not been changed for correct significant figures, and then asked to revise that into the correct answer. To solve for 102.0 grams, which has 4 sig figs, divided by 25 mils, which has 2 sig figs, that yields a calculator value of 4.08, which rounds to 4.1 grams per mil for correct sig figs, 2 sig figs based on the 25 mil value. Here are some more things that will help you as we work with multiplication and division with correct sig figs. Round the answer to the same number of significant figures as the least number of sig figs of any value that was multiplied or divided. Often, but not always, the original or given value for factor label method will determine the number of sig figs in the solution. For example, starting with 2.78 kilograms and converting to grams using the conversion below, 2.78 kilograms times 1,000 grams over 1 kilogram equals 2,780 grams, which is correct with the 3 sig figs shown because 1,000 grams and 1 kilogram are exact values and have infinite sig figs. So the 3 values from the given value of 2.78 kilograms is the least number of sig figs. Now you're going to go to the Google Docs and complete multiplication and division practice in section 6, that's U through X, following the instructions for completion. Pause the video now and come back after you finish those. Welcome back. We're continuing with calculations using correct significant figures. And now we're looking at conversion problems. So you learned about conversion problems already in chemistry earlier this week. When we work with conversion problems, the significant figures are usually, but not always, but typically determined by the significant figures in the starting or given value. All prefix conversions or conversions within the metric prefix line are exact values. For example, 1 kilogram equals 1,000 grams. So that is an exact value and has infinite sig figs. So practice the conversion problems on the Google Docs, and you're going to pause the video now while you do that. That will be section 7, following Y through Z, and completing the conversions. Be sure to show your work. You can use a slash for a divide if you're showing that in your conversions. Welcome back. Now we're going to look at some combination problems that use addition and subtraction and multiplication and division. So the thing to remember with this is when you finish a type of operation, correct for sig figs before you go on to the second type of operation. So if you add values together, correct for sig figs, and then use the corrected value in the multiplication division that happens afterwards, or vice versa. Complete the addition, subtraction, and correct for sig figs, then multiply and divide and correct for sig figs. For example, when determining density, knowing that density equals mass divided by volume from water displacement, if we start with a value for the water volume of 31.7 mils, and then put in a piece of solid that then changes the volume that we can read for the water, we would have a final volume of 35.9 mils. First, determine the volume of the solid that was added to the water. That would be final minus initial, so 35.9 minus 31.7 mils. So the solid that was added had 4.2 mils as its volume. Then to solve for the density, we divide as follows. If the mass was measured at 31.4 grams, then divide that by the volume at 4.2 mils, which we just found, which yields a calculator answer of 7.4761905, which should be rounded to the least number of sig figs. That would be 2 sig figs from the 4.2 mil value. So the correct answer would round to 7.5, and the units are grams per mil. Now you need to go to the density practice. You can look back at the information that I just worked with for this document, or sorry, for this presentation. Follow the instructions, complete the density practice problem. After pausing the video, return when you're finished. Welcome back. Here's another combination problem with addition, subtraction, and multiplication division. It is for percent error. The percent error equation is our percent error equals our error, which is the absolute value of our accepted minus our value that we measured. And then we divide that by the accepted value and take it times 100. First, we calculate the error. We take the absolute value of the accepted minus experimental value and adjust for addition, subtraction, sig figs. Just a heads up, sometimes this will be only 1 or 2 significant digit. Then we calculate the percent error as a multiplication division problem and round the solution to reflect the least number of sig figs from the percent calculation. So I'd like you to go to your Google Doc now and complete the percent error practice in section 9BB, following the instructions for completion. Pause the video and return after completing that section. Welcome back. Here's another set of problems. We're going to look at averages. Averages are determined from a counted number of items or trials and do not have sig figs determined by the counted number because that's exact. Okay? A counted or exact number has unlimited or infinite sig figs. The sum of the measured values adjusted for addition sig figs will then determine the sig figs for the average. Go ahead and do the average practice. There are two problems here in section 10. That will be CC and DD. Pause the video and return after completing section 10. Welcome back. You have now completed the significant figures packet. I hope you've completed it. You're going to take pics and then submit the pictures of your packet. Once you do that, you will have access to an answer key. Okay? You should check your answers against the answer key, which is the next thing in your sequence. And when you check the answers, you should make corrections with looking back and getting some information from the previous section, or even going back through some of this PowerPoint presentation. After you submit, your teacher will look at this and grade it on correctness. So we will be looking to see how well you did. If you would like to resubmit after you correct the values, and also after you talk with your teacher, perhaps to clarify some of the information about significant figures, then you may resubmit and your teacher will relook at that value and you may have an improved score then. So you may resubmit for a better score. Thanks for listening and good luck with the sig figs.